Okay, welcome to Max Math. What is it? MC 1308, so the eighth class for the year. We're going to be covering mathematics and mostly vectors as far as it goes in the in 3D Studio Max. But again, this is this isn't really necessarily a 3D Studio Max class so much as it is a straight up mathematics class for 3D. The math we're going to be discussing is math. It isn't max math, which is kind of misleading, I guess. I think it's kind of stopped as much as it used to be, but I used to hear all kinds of comments like, Euler rotations don't work that way in Maya or some other piece of software, whatever it was. And it's like interesting because Euler is not some random thing. Euler is a guy. He's a mathematician, and he developed the mathematics for Euler rotations. As well as dynamics simulation math and all kinds of other stuff. Lived in the 17th century, as David just pointed out. So the math that we use is actually funny because a lot of the mathematics, if not all of the mathematics, were like from the 17th century and whatnot. Long before they had computers. So realistically, a lot of what we do, probably most of what we do, is was worked out by some mathematician who just had it in their head and never could actually see it working or doing anything useful. So it's kind of, I have no idea how they did that, right? Supposedly the guy who figured out quaternions was walking along over a bridge one day while he was out on a date, supposedly, realizing that the Euler solution for rotations wasn't that good and came up with quaternions and scribbled it down somewhere. And it's like, okay. So we're going to start trying to discuss how some of this works, and most of it's going to be about vectors and dealing with the vector stuff, because that's where a lot of it sort of lands and starts from. So let's get going on that. First, we're going to take a look at sort of dealing with vectors and unit vectors and everything. I should ask quickly, how many people have worked with vectors so far in Maxscript or whatever, and started, dealing with the mathematics of vectors? Anybody here played with it at all? Or I know that Valmore and Kevin have to have had, because they were both students of mine some years ago at Humber College, and being TDs, I would have beaten it into them. But anybody else? Good times. Yeah, glad you think it was good times, Valmore. You have, and then Harry, what have you used them for? Okay. Interesting. I don't do it that way, but all right. Well, maybe I do, actually. I have to think about how I do it. Yes, well, I use matrix calculations for it. Okay, so which is really, a whole bunch of vectors and whatnot. So let's take a look at what a vector is. A vector is a point in space. Essentially, and it denotes a couple of things. A vector is just a spot, a dot in space, and it can give you direction. You can get angles from it. You can even get a magnitude from it. So you can actually get magnitude, like a speed from it. Sorry, David, connection flashed. Is everything okay there, David? Okay, good stuff. So let's just pop over to Max here and just have a look at a quick vector. I'm going to be using Maxscript obviously a lot for this, and I'm going to be using a lot of sort of objects to represent things as we go along here. So I'm going to create a sphere here, and I'm going to give it a radius of 0.5, so it's going to be really quite small as it goes. And so a vector, being just a point in space, is literally just the position of this sphere for all intents and purposes. But what we can use that for is the ability to be able to point in directions. This is the origin that we're looking at right here. And this origin then points off to, and let me just get my pen. So there's our origin. That's our world 0, 0, 0. And here's a vector, a point in space basically that we're going to be utilizing. And what we're going to be able to do from this is we're going to be able to make a direction vector, okay? And we're also going to be able to make a unit vector, and you'll be able to see what the difference of those are as we start to work on it. Let me just erase that and turn that off. So back to our Maxscript, and just for now I'll just use the Maxscript listener, and I assume everybody is familiar with this, and I don't need to discuss Maxscript at all. So what we're going to do is we're going to grab a vector and check its length. So I'm just going to say v equals, and we're just going to use a position of this current object here, and I'm going to call this object v1. How's that for now? And we're going to call it vector1. So to get access to that, of course, $v1 dot pause, and it returns to us its point in space that it currently sits at. And you got to be a little bit careful when you do dot pause. Sometimes it'll return the position of the object and whatnot, not necessarily in world coordinates and whatnot. Transform dot pause will get you the full, make sure I want to know the actual world space position of this object. So I tend to always go through the transform instead of just dot pause, because I've seen issues there that I suddenly go, what's going on, what's wrong here, and I suddenly realize that I'm not getting the true world position from something. The object's transform dot position will get you that true world position all the time. So sort of just get used to going down that road. Now, something you can do with this is find out its direction from this, from the center point here of world space right now. In a sense, you can draw a line that travels through from here and travels up through, not a very straight line, is it? So the sphere was drinking as it was doing this. There we go. So it kind of goes up through the center, and it can give us a direction and also a magnitude. How long is that vector, and how far does it actually travel? So we can get the length of that vector really easy with a nice command called length. And we say length v. Oops. And I'll just put down the next line. And what length is getting us right now is it's telling us that from 0, 0, 0, no, it's not grease pencil for Max made by Paul. That's actually through GoToMeeting. I got a much better one coming sometime, maybe. The length now is being basically told us that the length of this vector, when you ask for the length of a vector, it's from the origin, from 0, 0, 0 to this point in space, is currently right now 14.8 units in length. Now, we're currently dealing with a vector that's always from this origin right now. Well, you can actually make vectors that aren't from that origin and from somewhere else, essentially. So the other thing we want to be able to do is get a unit vector out of it. Now, what's important about a unit vector is that a unit vector is normalized, is the way it's also referred to as, to 1 unit in length. So if you remember the good old Cartesian graphs of whatever it was, grade 8 or something, that was a very long time ago for me. We've got our typical Cartesian graph here, and we're calling this 1 unit from 0 in the center to out, and out is 1 unit. And you'll notice that we have what's called a unit circle as well. It's 1 unit in its radius coming out, and we've got a point anywhere along that curve is actually a point that is 1 unit in length. It's not 1 by 1 out. So let's take a look at that. So if I actually take our object here, and in x and y I do 1 and 1, and we get it in nice and close. We're now out on that Cartesian graph now, straight out, up 1, cross 1. But if we check the length of our vector again, so let's just go down and get our vector and check the length of our vector, we're 1.41. So we're not actually 1 unit in length yet. So we can actually normalize that vector with a very simple command called normalize. So normalize v will return a normalized vector that's 1 unit in length. And if you notice, that value there looks very much similar to the value that I had in my graphic here. So if we go out 0.707 along x and up 0.707 in y, we end up finding that point in space right there that's 1 unit in length. So to normalize this, right now the position of our object isn't actually normalized. I could just simply say $v1 dot, and you can't set the dot transform dot pause property, so you have to just go through and say dot pause equals the normalized vector that we grabbed, and now this object is 1 unit in length. So we could actually check length $v1 dot transform dot pause, and let me just clear that, and you'll notice now it has a unit length. This is really important when it comes to 3D, and as you get into it, you're going to start realizing, if any of you have ever read anything I've ever written about scaling stuff, especially in character rigs and whatnot, you'll always know that I've said just don't do it. And there's good reasons, and you're gonna, if you don't know why, you're about to find out as we go through this, and you start to see what's going wrong with the matrices and whatnot, and the vectors that are happening here. So there's a quick explanation of a vector and a unit vector. Everybody good so far? I don't imagine I've lost any of you at this point, but I know I just need to cover these things. Okay, so let's make another scenario here. And I'm going to call this one just V3 for sake of ease, and I'll make it blue. And so what we can do now is we can start looking at, I'm going to go into perspective, or sorry, user at top. That might be easier to look at. That's probably a bit easier to look at, I hope. And so what we're going to do is we're going to set all of our information that we're going to generate onto V3 here, and we're going to generate that information using V1 and V2. So we're going to basically generate it from these two. So often what you're going to find is you're going to need to be able to get vectors from an arbitrary point in space, and we're going to call that V1. So basically, here's our origin now. V2, one second, David. V2 is going to be our vector we're pointing out to from V1, and we're going to see what the result of that is on V3 and what it actually does. David, quick question on the expression controller. We don't have a normalized command, do we? No, you don't. You'd have to do the normalized command yourself, which I'll show you in a second. But I'd just use script controller anyways. So what we're going to do is we're going to do a little bit of simple math here. And if we go back to my wonderful graphics, we can take a look at these. And so here what I've got is what I'm calling them P1 and P2 for points. Basically what we're doing is we're taking our P1, which is our V1 in our scenario here, and our V2, and we're doing a little bit of quick math, which is P1 minus P2, and we're getting a direction vector that's going to be from the origin 0, 0, 0. So let's just make that happen real quick. Let's call it V equals, and we'll go $ V2 dot, I'll just go dot pause for make it simple and fast right now, minus because I know they're all in world spaces at this point anyways, V1 dot pause, and I'll set that value, but let's just set it directly on this. So why don't we do it directly and say $ V3 dot pause and set it. So what you'll see now is that this object, blue object, is now from the origin exact same angle that this red object is from the green one. So if I change this angle over here and run it, you'll notice it sits straight up from it. Its length from it remains the same. So we're getting this length from these two here. So it's actually producing a value that's from the origin of world space. We can move these anywhere we want, and that won't change the result because that result is based on getting us a value from that 0, 0, 0 point. This is again going to be very important as we move forward into the next steps of our math here. Now what we can do is we can normalize that, which is really good, and this is going to be important as well. We can then say something like normalize command in max and normalize that vector, and you'll notice now that no matter how far we move out the red one, that blue one's always going to be 1 unit in length, but pointing in the same direction. Okay, so it's pointing down that same direction as we are from our green to our red sphere now. And again, this is going to be important for building, you know, some basic mathematics to go from here. Okay, this is basically the starting point of dealing with a transform matrix and building one from objects. You wonder where this might be going or what this could be used for at this point. I've actually written, you know, straight up in Maxscript again, the ability to be able to port marker data from mocap suites. So not the cleaned up, not data that's been turned into rotations and whatnot and exported out as you know FBX files or whatever else. I've been able to take the raw marker data, so just the markers flying around in space, build transform matrices from sets of them, and apply them to the controllers on objects, and have the character basically chase marker data around the scene. And essentially what I'm doing is I'm doing what Motion Builder and whatnot does directly in just in Maxscript, and it worked in real time. Actually, you could scrub the character through and it would chase the markers in real time around the scene. It was kind of fun to watch. It was one of those things you write and you go, wow, I could just sit here and play this over and over and watch it happen. So there's some basic vectors, and so here's normalizing. So the mathematics of normalizing, if you wanted to do it in the expression editor, as David was asking, you'd have to do something like this. I think there's a square root function you can get access to. It's been a long time since I've used the expression editor. Actually, I try and avoid it just because it always limits me in some ways and causes me more grief. So to get the length, you need to first get the length of a vector. And again, there's no length command in it, so that I'm aware of. But basically, you need to get the length. And to do that, you need to write a square root of values. And here what you're going to find is if you start trying to do this in Maxscript, it'll get slow. You're much better off, probably, if you need to do this sort of thing, doing it in the script controller and allowing Max to deal with the length command and just dealing with all of it that way. It'll run way faster than it will having to parse it through Maxscript. And doing this sort of math together. Just adding up values is slower than running a square root, I've found. I actually tried creating what's called the, what do they call it now? The taxi cab length. I forget how that refers to, but if you think of streets, more of a North American thing, I think, because all our streets are dead straight in a grid. Finding the distance to an object based on taking right and left turns is a fast way mathematically, because you don't need to use square root to do it. It's inaccurate, but if you don't need to know the exact length from point A to point B as the crow flies, you can get really close averages and understand whether you've moved further or closer, and it's faster mathematically. I wrote that out in Maxscript, and it actually ran slower than the square root function did in C++. Okay, so there's no point in going down and trying to write it yourself. You then normalize it. Normalizing it, basically, if you take the direction vector, so the value, okay, of the vector out here, the direction vector, and you divide that by its length, you'll get a normalized vector returned, and that will return it. So there's the mathematics behind it, but again, not something that you really need to be using a whole lot and sort of diving into. So let's first talk about some of these calculations and what they're going to do and how they're going to react as we start looking at trying to build a transform matrix and getting into it and what we're going to do with all this stuff. So first off, positions are calculated in the space of their parent. So generally, if you have objects parented together, and you look at the dope sheet for values, you'll notice that those values are representative of their parent object. So if we take a look at the object here in red, which is our sort of end target, it's our V2 of it, it's currently sitting at 5.6, 6.5, and 0 in Z, and that is away from the 0, 0, 0 position. Watch what happens to the value as soon as I actually parent it up and link it up to V1. Watch the values change. I don't know if you can see it, but you just suddenly notice that the values jumped and changed. If I move V1 around, you'll actually notice that the values of V2 don't change. So I'll just move it and go back to V2. You'll notice that the values didn't change. Do it again. You'll notice the values didn't change. So the end value of position is relative to its parent. It's an offset value from its parent. The transform space position value, okay, is not. It's always returned globally. So it will always return this space off of here. Let's see if we can make this watch, it'll call me a liar too, sort of mathematically here. So $.pause, yeah, so the $.pause is still returning our global value, as it should, but like I say, sometimes it doesn't. But if we went down to that end controller, it would give us this value here. So if we dug all the way down to our end XYZ position values, it would actually give us those value. Controller dot will actually return it. So what we're asking for is the position controller here and its value. And you'll now notice that it's actually giving us the value of the controller downstream, which is that offset value. And its global value obviously is different. So that's something to note. Also, something to note is if you were to actually, this is something that people do, is they take it and they rotate it, and then they want to actually move it along its local y-axis here, and they want to actually type in a value. So they take this and they say value.y, and I'll just go plus equals 20, or actually maybe it won't go that far. It'll probably fire it off to no man's land. I'll say 5. Watch direction this travels in as I do this. It traveled straight up. It didn't travel out along its y-axis. It actually moved straight up and not out. And that's because the parent, it's all based on its parent. So again, if I now take the parent and rotate it, and I could even rotate this one even more. So y is pointing off in this direction for the object I'm setting it on, but its parent points off in this direction here. So if I run this again, you'll notice it's actually going in the direction of the parent. Okay, so that one I often see posted on places and people going, I don't get it. Why is this happening? And I'll just reset those so I don't get confused as I do things. Now, if we go back to the rotation, it's calculated in the space of the parent node as well, sort of. As we start getting into this, we have to understand how, and it's actually a little more complicated. So rotations in themselves are a pain in the ass when it comes to 3D. It isn't, again, Max. It isn't any specific piece of software. It's mathematically, rotations are problematic at best. And more importantly, the ones that animators want to use the most, an Euler rotation, are the most problematic. Okay, they're actually really bad mathematically. Okay, they don't work very well at all. And unfortunately, they're the ones that actually give us the proper function curves, or at least sort of the proper function curves for animators to work with. Now here's where the problem lies. An animator, especially when they're new, about 2 years into their career, will finally go, no matter what piece of software in that, hey, these rotations are broken. And of course they've run into what's called gimbal lock. And so let's just make gimbal lock happen here and just take a look what's going on. I'm going to use a box for this. So here's my box. I'm just going to make it, we'll just make it 1, 1, 1. And we'll make sure, just for sake of argument, it's sitting at 0, 0, 0 position for no particular reason. And we're going to take a look at the rotations. So if we rotate this object, and we rotate it over, say just along the X, for instance, right now, turn on my angle snap, and I'll go over 45 degrees. You'll notice that what we've got is 45 degrees around X, and we go, hey, great, this is fantastic. So we start working in local space, because that's what we want to see, and we start rotating around Y, and we go 45 degrees in Y, and I let that go at 45 degrees in Y. I don't know if you can notice the heads-up display there right above my mouse. It says that I haven't rotated around X or Z, only around Y, yet when we look at the mathematics here, I'm no longer rotated around 45 in X. I didn't get 45 in Y, and in fact, I've got 35 in Z now. So there's a problem, and the problem being is that it's all relative to its parent, but it's also relative to an axis order in Euler rotations. So if you go over to your motion panel, you can see that, and you pick rotation. You can actually see this axis order, and this is really important to manage and understand what this is doing. If you think of the order of operations here, I'm telling you that essentially rotations are based on the parent. Well, they're not. They're based on the axis order, then the parent. And in fact, an axis order of X, Y, Z would be like actually having three objects. X is parented to Y, Y is parented to Z, and Z is parented to the node that is its parent. In this case, that's world space. So there's actually a hierarchy of objects happening here, X being the child, Y being the middle child, Z being the most parent. How's that? So if you think of it in that sort of order, you're going to run into gimbal lock really quickly, and we can show that very quickly by going in, just putting together three objects, one on top of another. We'll just do a link up. So this is going to become our X, Y, and Z. And if you consider this, then, that we can only rotate each one in their given axis and only allow that axis to be the one that's going to be rotated around. So Z is going to actually be rotating around Z only. Y will only rotate around Y, and X will rotate only around X. So right off the bat, you can see the hierarchy happening here, that when I rotate X, it doesn't rotate the other two axes. So when we actually see this local axis that you see right now, because I'm working in local still, well, you're not actually, Z didn't rotate over. It's not off on an angle like this. So when I rotate around Y, which I can't do there, I have to do it down here. When I rotate around Y, you'll now notice that the end result really is actually cocked over on some completely different angle. If I then rotate Z, I'm actually rotating the other two all the time. So the end result ends up being sort of this combination of these axes together, right? It's essentially X plus Y plus Z for all intents and purposes. It's a little more complicated than that mathematically, but basic idea. And then that's applied down to the transform matrix and turned into world space. Now the other way to think about rotations that is better is quaternions. I'll get back to scale in a second because it's real easy. We're not going to get heavily into quaternions because, quite frankly, I try and avoid them just because it hurts my brain to think about. But again, I forget who the mathematician was now, I forget his name, who figured it out. He basically said, hey, there's this problem of gimbal lock, of having these three different axes in an order added together. And it's causing a problem. So what we're going to do is we're going to use what's called a unit sphere. So remember we talked about the unit circle? And if you look at this, this is a unit sphere now you see drawn out here basically. It's 1 unit in radius all the way around. And so that means that any point on that surface is 1 unit away from the origin, 1 unit away from that outside of the center point to the outside of the sphere. It's 1 unit in length. So we're back to these vectors again. Now it's again a little more complicated than this. When you look at the quat values, they're definitely more complicated than what I'm about to suggest, but this is the basis of understanding of it. That point on the surface is a vector. So it's actually a position point that you can pinpoint. There is no XYZ rotation axis in a quaternion whatsoever. They don't exist. The fourth value is basically a rotation around that point. So a twisting around that point in a unit value as well. And so what you're getting then is this ability to be able to pinpoint a point on a surface and a rotation around that point. And you don't run into gimbal, essentially. There's no gimbal problems whatsoever because you're not having to add up axes. Vectors are very accurate and very easy to work with. A point in space is a point in space. And it doesn't change at all. Okay, it doesn't change when the next one down gets rotated. You could always find that point in space. David's right, they're awful to work with from an animation standpoint, because the problem with quaternions, and this was always a funny one, was a number of years ago, I guess some piece of software, I can't remember which it was, it might have been Motion Builder long before they bought it, had quaternion curves. And the Max people found out that it had quaternion curves, and back then biped only had quaternions. You couldn't work with biped in Eulers, which still I don't think works very well to this day. You could only work in quaternions, and the animators were freaked out because essentially they couldn't work with their curves. And so Autodesk said, okay, and they put in quaternion curves, and everybody looked at them and went, what the hell? Because they don't make any sense, because everybody thought they were XYZ axis. They're not. So the thing with the unit vector is when one value of the vector changes, X, Y, or Z, the other two have to change as well to find that new point on the surface that is 1 unit in length. So if you can imagine, any point on the surface can only be represented by one vector value, essentially. So if you look at function curves for, I can probably just do it right here. If you look at function curves for a sphere in a quaternion rolling over and over in a ball in a straight line, what you get is X, Y, Z, and W are the values. You'll get X, you'll get Y, you'll get Z, and you'll get W. And that's a ball rolling around in a circle, in a straight line, whereas in a quaternion, rolling along X would look like that, and that's it. All the other two axes, if it was going in a straight line, the other two axes would be flat. So the quaternion function curve, it looks like a sine curve as it goes along, and it's a mess. Yeah, then imagine dual quats. So it's not very good for animators, but it's very effective when it comes to rotating objects and being able to calculate the rotation of an object. In fact, there's only one really major problem with them, and that's that if you take this units circle here, and let's say we started at the top, and we rotate our object 180 degrees and end up at the bottom down here, which way did we rotate? That's the problem. Which way did we actually go? The fourth value will tell you that we have an angle that we can go through, and essentially that angle is going to tell us that we can either go that way or we can go that way. So we actually have two solutions for the rotation to get to a different point. Now, if it's just like 0.0001 off to the one side, it'll take the one route and not the other. Even if you rotated it this way, it'll take the other route. The best thing you can do is rotate in pieces. So maybe rotate a third of the way, and back a third of the way again, so it actually understands which direction it's going to go around the rotation. So again, that's their failing and problem. Now, note, of course, they managed to put a man on the moon with this math, right? So it can't be all bad. Let's just go back to scales. Scales are actually pretty easy. It's just a multiplier value. So you'll see the scale represented here as 100, 100, 100. I wish they didn't do that. That's actually a kind of a misnomer. The value isn't that. So $.scale is actually 111. So what they're showing you is the percentage of scale. It's 100% scaled right now. And so 111 is the multiplier value, and really what you need mathematically. So I wish it didn't, show. I don't know why they, do this in Max. At time to time, you'll see the values that are actually returned to you that you're looking at are actually different than the ones that are returned to you when you actually call it via code and go and get the code. It's a little bit of a pain sometimes when you're trying to look at things and figure out what to do. But it's just a multiplier value. We'll see how that adds up and adds into it as we go. So let's start taking a look at a transform matrix and how this is built and what it actually is, because this is where everything comes down to. If we look at Max and we look at the transforms of the box that we currently have picked, we've got our position, rotation, and scale. We know that our rotation has a hierarchy of Z, Y, X. It's actually backwards from what the X, Y, Z is. So you basically got child, middle child, parent. That gets condensed down into a quaternion, by the way. So if we actually check the rotation value on this object, $.rotation, it'll actually return to us a quat value. And that quat value, and we'll just again rotate this over around 45 in X and check the rotation, and you'll notice that we get this crazy 0.382683000, 0.92, okay? So it's this crazy bit of higher level math that is used to generate that. 0001 is the starting point. So that gets condensed down. The Euler gets condensed down into a quaternion. The position stays as it is, and the scale stays as it is, and all three of those values get put together to build a transform matrix. That transform matrix is very important because when you actually go and grab an object and scale it or move it or rotate it, it's that transform matrix that's being passed on to its children to calculate their new position. Because again, don't forget, 3D is just a pile of math. There's no physical linking here. One of them isn't holding the other one's hand. It's just math. So when I'm rotating this one, what it's doing is it's taking the values that I'm inputting, condensing them down into a transform matrix, passing that matrix on to the next object and multiplying it into the object's transform, and then rotating the object and moving the object accordingly to its parent. So a transform matrix looks like this. It's actually contains all position, rotation, and scale values. And it's not what most people think when they first look at it. So the way a matrix actually structured is, it's got, in Max, it's called a matrix 3 value. And it's theoretically, it's actually 4 values, but I'll describe that in 1 second. It's got 4 components to it: X vector, Y vector, Z vector, and a position value. The one that's easy to understand is position. This is the position of the object. In world space, by the way. Again, this is always being returned in world space. So when we said $.transform.pos, it's this value here that's being returned and kicked out to us. The ones that get complicated for people to understand at first is the X vector, Y vector, and Z vector. These 3 vector values are vectors. They are not rotations, and they are not scales necessarily. Okay, they are vectors. They're points in space. Those points in space are calculated using the rotation and scale of the object that we input. So to look at this, if you take a look at the X vector, here's our position value, dead center. Okay, in this case we're at 0, 0, 0 world space. Here's our first vector value. First vector value. And that vector value goes out from the center of world space. It's 1 unit out along X. So none on Y, none on Z. So it's 1 unit out on X, none on Y, none on Z. The Y vector, same thing. None on X, 1 on Y, 0 on Z. Okay? Same thing with Z, 0, 0, 1. So it's 1 up, straight up above it. So those vectors are then just calculated exactly the same way that we were doing vectors to start with then. So they're calculating out from its origin. the origin is always this point here. So when we were back in Max and we were talking about calculating essentially our vector, which was our blue one, from these two, this was our origin, green, and this was our vector pointing out here. Okay? And then it was calculating out a direction vector. Now, it isn't normalizing it. Are these, David asks, are these vectors always orthogonal? They should be. So orthogonal meaning, are they always square to each other? So are they always square? If not, you actually get a skewed object, which is kind of fun to play with. Yeah, it's easy to skew a matrix, exactly. And that's exactly what we're going to do, is we're going to make a transform matrix and have some fun with it. So what we can do is we can actually calculate these and start playing with it and seeing what it actually does. So let's actually just go and do this, since we've got some objects here to start with. I'm going to center my pivot here. Effect pivot only, centered object, just so it makes the most sense. And I'm going to take this object then, and I'm going to just zero it down to world space. And we're going to take our Z vector and we're going to set that into its location that it's needed. And that is going to be 1 unit up. And we're going to take our, we'll take this one and we'll say 1. And we'll take this one and say 1. So, oops, where did my, hey, where'd my, oh, there it is. Typed in something wrong. There we go. Oh, that's right, it's linked. Thank you. Thank you. Unlink. You know what I'm going to do is I'm going to turn off realistic as well. And I'm going to make this totally different color. We'll just call it orange. And so let's take another object and set it as our position value. We need one more circle, let's say, for our position value. And we're just going to call this P for position. And I'm going to set that at 0, 0, 0. And I'm just going to make it a little bit smaller just for sake of argument. Okay, so what we've got now is a box, and we're going to input into the transform matrix of this. We're basically going to build a transform matrix for this box using our 3 or 4 other vectors. Okay, so we can then take a look at the position vector is going to be the one in the center that's orange, and then our 3 other vectors that are out from it. So this will be pretty straightforward to do as a simple starting point. I'm going to take the transform of the box and assign it as a controller, and I'm going to make this a transform script. So we've got a script controller here now on that object. As we were discussing, it's pretty easy to manipulate and skew an object and make a mess of it. I'm just going to evaluate that. I just made the x vector 1, 1, 0, and you'll see that we've skewed it. So let's actually rebuild this, and let's make a vector for this. I'm going to call this xv. I'm going to call one yv and zv and pv. And then I'm just going to set the values on them so that I can actually get access to each of these. So I'm just going to grab that object. I'm going to say assign constant. And a real quick way, if you didn't know, you don't have to go through this pick dialog thing for a node and whatever else, or even a track. You can just type it into the assign constant. xv, I'm going to say assign constant again. Since it's picked, make it real easy. And the final one, assign constant. And we've set them. How about that, eh, David? So what we've got now is a bunch of values we can input. Yeah, that list can be a real pain. It'll highlight the one selected, but you got to, I've often got character rigs with 1,000 nodes in them. Good luck finding it. So you can literally just type the whole path into a controller to get your controller, or the name track to get to set it as a track. And of course just the $ for whatever selected, or just name the object's name, and then it'll actually hold reference directly to that object's. And again, changing its name won't affect it anymore because it's actually held reference to the node directly at that point. So let's actually start setting this up and replacing our matrix values with our vector values that we currently have. So first I'm just going to start with the position value. I can call this PV at the end and say evaluate. And of course that's going to work. So pv.pos will get us our value. And I'm just going to go and grab, and you'll now notice that if I move that around, it's actually moving the object because it's being moved with that position. If I rotate that point, nothing happens because we're not actually changing our vectors. We're not building that. So let's actually set these all up then in a row here, and we're going to say xv.pos and yv.pos and zv.pos, and we're going to evaluate. We should get back a nice unskewed transform going on again here. Now what's going to be really cool is you can have lots of fun with this now, because you can grab this and you can actually go and do all kinds of crazy stuff to it. So this is actually going and inputting and changing this first value and allowing you to be able to input and build a matrix that is obviously a bit of a mess at this point in time. So what you've actually kind of starting to build here is a look at constraint. Essentially the box is looking at down the x value right now as I move it. The problem is it's skewing and making a complete mess of it, and obviously not doing what we want, and causing us some nasty grief along the ways here. Same holds true for all of them. And even more importantly, we have a bit of a problem because when we move the position around, the other ones aren't kind of traveling with it, which really is what they should be doing. Those vectors don't stay behind. So in a transform matrix, when we move the object, we actually just check it and just do some math here for a second. And we'll just check it on our object we've got. We say $.transform and take a look at the transform value of it. And that's almost 0, by the way. Max has these lovely rounding issues because it's single precision math. You'll notice that basically the values are, the first 3 values will remain the same. Even if I move it over and check it, those all stay the same, position changed. So the way you can think of these vectors is the position value is the origin. So they all need to be sort of linked up to it and getting you that origin value from it. Now they are currently right now, in a sense, they're staying because we're just getting its position value, and it's staying, its vector is relative to its origin, which currently right now is down at this point here. So we could go in and take each of these and link them in, and then we could move around, but doesn't seem to work. It's doing some really crazy, ugly, skewy, messy thing now. The reason it's doing this skewy, ugly, messy thing is that we're actually getting the position values of these vectors in world space according to the center of world space. So as we drag that center point out away, we're actually getting this, every single one of them is skewing and going messy and doing something crazy. Okay, so rotate it around. Ooh, that works. Okay, so it's actually rotating now because the vectors are rotating and inputting them in. So it's our position isn't working. So we can try a couple of things. We could try doing this. We could try going, well, let's do what we did before. Controller value. And that's the value offset from its parent, if you remember. So now if I move it, hey, guess what? No more skewing. It's actually working correctly. And then if I rotate it, oh, doesn't work anymore. So what we're getting here now is a problem with our math a little bit different. The position works because the vectors are moving along, and the origin of this vector is relative to its parent. The problem is that vector is also relative to its parent when we rotate it over, and it's still saying it's actually, the z is still 0, 0, 1 up from that object. It can't be, actually, because the transform matrix needs to be in world space. So this isn't working right now, doing this, having these being calculated this way. So what we need to do is we need to do something a little bit different. Let's just get rid of those for a moment. And let's just input those that way. I don't know if you guys can see that. Unfortunately, I can't scale the text in here. It doesn't work. So let's go and get those values and do what we did before and find out what their vectors are, even though they're parented up to it in a sense, and moving around from it. So what we can do is we can actually say, let's just say, let's just call it straight up x equals. And what we're going to do is we're going to take p2 minus p1, just as we did before in a sense, or v2 minus v1 that we did. So we're going to take our vector, and I'll start with the x value. Should be pointing over here at our x value. I thought I made this guy yellow or orange or something. Maybe I didn't. There we go. Minus the actual position of the object. So PV dot pos will give us an x vector now. And so it'll give us that vector from that origin point. So let's just call this x now. And we'll grab this one, and we'll start to rotate it. So you'll notice it rotated, and it's actually skewing still. So the rotation is going to work, we know that. So let's try it with each one of them. X, Y, and Z. And we're going to call this Y and Z. And Y and Z. And we can move it again now. And we can rotate it again now. So now what's happening is we're actually going and getting the vectors back in world space. So if you remember when we went and did that bit of math back here, where we went and grabbed that value and it gave us a vector off of the center of world space. So in a sense right now that's the center of our transform matrix. This is one of our vectors sticking out from it. We're doing this little bit of math, getting it from the origin so that we don't actually get that wacky skewy thing happening. So now we're able to actually rotate our object in a sense, but that's not actually how it works. You don't actually rotate the position value. You rotate these. So even though that math works incorrect on how it works, when you go to rotate an object, let's say around the x, what actually happens is this. Z gets moved over here, Y gets placed up on top. So what we'd actually have then is -1 and so what we've done is just inverted them. The y-axis is actually 0, 0, 1 now. The z vector, the z vector is actually 0, 1, 0 to rotate our object around. So let's go back. Here's our normalized and orthogonalized default matrix. Okay. If we take a look at rotating around the z-axis, what we're actually doing is moving the two vectors into new locations, and in this case 45 degrees. And see these numbers that we were looking at before? So they're normalized vectors that are being moved around. So as we rotate our object, it's actually calculating these vectors from the Euler down to a quaternion to a vector and placing it there, and it's multiplying that length of that vector by the actual scale value. Now where is that scale value? So the next one then shows us the exact same thing. We've rotated around Z 45 degrees, but we've also scaled it by half, and we've pulled that scale value down. So if we go back one, if you notice that the Z didn't change, the Z vector didn't change. We're actually moving XV and YV. But as soon as we go to a scale, we've moved XV and YV, but we've also moved ZV now, and we've moved it down by half. And you'll now notice that what we've got is this vector that's moved down and in. So when I say don't scale things in a rig, don't scale objects in a rig, is because this matrix is what is passed on to the next objects, and you can run into all kinds of nasty problems as soon as you start making sure that these vectors are no longer normalized. So this Z vector isn't normalized anymore. It's not 1 unit in length. And we can see that really simply with this really simple example I show people. I'm going to take a couple of boxes, and I'm just going to make this one not as high. We'll call it 1. And for whatever reason, actually, we'll call this 1 as well. Let's call them 1, 1, 1. How's that? We'll do it really simple. Just delete that. So we suddenly decide that, hey, this one needs to be longer. So I'm going to scale it up in Z and just scale it up, and you say, hey, that's great. I want to take the top one now, which I'll just color code red, and I'll link it up to the parent. No issues, right? Hey, this is great, no problem. This is exactly what I'm looking for. Then I go to actually rotate our object, and we get this nasty mess happening. So everything is relative to its parent when it comes to the transform matrices as well. The transform matrix of this is being calculated into this one to get its offset value when it's been moved and rotated. Because the parent was already scaled, this one was given a scale value as well, so it was actually calculating a scale value for it. And if you consider what's happening here is that, you know, if we pull this up as we did, we scaled it up and pulled it way up here somewhere, so it's like 5 times longer. It's like got a unit length of 5 as opposed to, sorry, not a unit length, a length of 5 as opposed to a unit length, which is 1. So it's way up here. And what's happening is because as it rotates over, so at this point here, that's now to the top, but as soon as it starts rotating, everything's relative to its parent. So if I go all the way around 90 degrees, what's happening now is the scale on the Z is being applied to the scale of this object along its Y, and it's scaling it up now on this Y-axis and pushing it out in this direction. And so as you go around, you'll actually notice, I don't know if you guys can see it. Let's see if I can see it. There it is there. I think you can see my, how do you increase the size? There you go. You can probably see my transform gizmo here is skewed. So what it's actually doing is it's scaling both of them right now. It's scaling Z and Y, and you're getting this crazy skewed value out of your object. So this obviously isn't what you want in a transform matrix. So we can actually make sort of a true look at constraint out of our mess that we have here and not get the skewing action going that we're currently getting and all of this. And what we can do is a little bit of math to have fun with this. So let's actually make a I've got a couple minutes to 11. I want to do a save. So let's actually make a look at constraint, okay? Let's do the mathematics now and take this and turn it into really what a look at constraint is doing. So a look at constraint is looking at a target object. We'll call that X by default. It has an up vector, and we're going to call that Z. So let's actually just reverse these again and put them back to where they're supposed to be. And we'll call that 0, we'll call that 1. And by default, a look at constraint looks up in world space, just like a camera does. It always points up, straight up. So Z straight up all the time in this case. Now, I'm also going to, yeah, that's fine. What we've got here, I'm just thinking about where I'm going here. It's kind of like, again, I always say it's kind of like chewing bubble gum and walking at the same time. Sometimes you have to pause and not bite your lip and sort of stuff. So what we're going to do is we're going to have it looking at x. We're going to have z as our up vector, and y we're going to calculate along the way. We're actually not going to use this value for y at all. So this is how it works. I'm going to calculate x. It's pointing straight at it. Okay. I'm not going to calculate y at this point, so I'm just going to comment that out and not calculate that. I'm going to calculate z pointing straight up. Now what we want to make sure as well is, because our target might be way over here somewhere, that our object doesn't go and scale on us. What we need to do is come up with a normalized, so normalize our vector. So if we normalize that vector, normalize, oops, I may just leave y in there for the moment, so I'll just uncomment that. So now that it's normalized, you'll see that it's skewing the box, but it is still trying to point it. It's really what it's doing is it's pointing at it. It's because our vectors are not becoming orthogonalized, as David pointed out. It means we don't have a right angle between the x and y right now, for instance. So we're getting that skewing value happening. And so we're also going to want to do a normalize on the z as well, because we don't know how far up it's going to be, because we might pick some object that's up in the air. So normalize those two. That one as well, so it can be anywhere we want. Okay, and it currently right now is also skewing the object. So we want to be able to look up and not have it skew. We want it to be able to look side to side and not have it skew. So how do we do this? So let's just, again, let's now calculate our y down below. And so to calculate an orthogonalized vector, so basically we want to be able to get when the x moves out and over to the side, we want to be able to find out where y should be, which would be about there somewhere. So we need to be able to drop it there. So what we're going to use is the cross product, and the cross product is just cross in Maxscript, and then we need to actually apply it in axis order around in a loop. So let me just get my little drawing pen. If we think of x, y, z, okay, if we want to calculate one of these, we need to cross the other two. And let's think of it as a circle of axes. So if we want to calculate x, we say cross y, z. If we want to calculate y, which we're looking at doing, we need to calculate z, x. If we want to calculate z, we need to do x, y. So if you do it the opposite way around, what you'll actually end up is with a left-handed transform matrix. We'll discuss that in a minute. So we're going to say y and, z, y. And we're going to calculate that. Cross. Oh yeah? Oh jeez, I'm an idiot. Sorry, x. There we go. And so you now notice that we no longer have this affecting it whatsoever. Okay, so what we're redoing now is we're actually calculating the position of this object for us, and it's actually returning that. Let's do a real hack. Okay, this is a real hack. Actually, we don't need to do. We might be able to do this. Let's actually say, just for sake of argument, so you can see it, yv.pos equals y. That might mess with things heavily. Oh, no, it works. So that's where that new position is being calculated now. Okay, so we're calculating up that new position right there. Now, what we want to do now is do it again, because as we go up and down now, we're getting this problem where you can actually see the y going in and out. We're actually not getting the z being recalculated, because the up vector should be sort of up as much as up can be, right? So let's just get this back to our unit vector here, 1 and 0. As we go up, this has to tilt over in a sense so that it's calculated over. So what we need to do now is we need to recalculate z. So z is going to be equal to the cross of our other two axes that we've now got, which is x and y in order, and evaluate it. And now what you'll see is we have, it's almost working. It's doing this strange scaling kind of thingy going on still. It's kind of rotating. It's not skewing. Problem is we haven't normalized our vectors. And just make sure everything gets normalized. Making sure everything stays normalized. There we go. So we can even, let's just go back and place yv.pars, or sorry, zv.pos, zv.pos equals z. So you can see us recalculating. This one could, I'm amazed that actually worked. It's kind of surprised that worked. Yeah, it doesn't allow me to move it anymore though. So I'll just comment that out. So there's our up, and our up is actually staying stationary. So at some point what's going to happen is, as we flip it over, you can see it suddenly flip around to the other side. So what you're getting is you're getting this case where we're starting off with the x, we're having setting an up vector, we're taking the angle between these two and we're calculating an angle that's square to the pair of them. So even if these two aren't square, in other words, one's up like this is square to both of these. So it's square this way and it's square that way on our graphs. And now what it's doing is then calculating this one. Now knowing that these two are square to each other, it's recalculating this one as a square out over here somewhere and placing that one square. Now the problem being is you pass that top point, it suddenly flips over because the square just changed its direction. So we now get a flip, just like you do in a camera. As you pass a camera over top of its target, or its target over top of the camera freaks out and spins around because it's doing exactly this. So, you know, if you can reset your up node, you can stop it from doing that. But you get that up node too far and it'll freak out and flip over again. So there's basically a look at constraint using your own matrix values and calculating it. So what I was doing with calculating mocap marker data is I would have a control object for my character rig essentially. I'd take a series of marker data points and I'd come up with an average point or something that would be used for the position. I would then take two other points in the marker data. Maybe let's say if this was the neck, this would be the top of the head, one of the top of the head markers. This would be one of the ones stuck on the front of the face or whatever, looking out in front of the character. And I would calculate the rotation based on those values. I'd have one that's fixed essentially, and then I'd have one that's an up node and a bunch that are calculating the position, and I'd calculate and create transform matrices for all of the control objects on the rig and have it chase the marker data around. So does that, guys, explain how a transform matrix built and where all the vector stuff comes from? I got to do a save here now and make sure that I save out my recording so that we don't lose it. And sorry, Harry, you asked a question there I missed. Is that dependent of the axis order in the motion tab? This has nothing to do with the axis order of rotation in the motion tab. We have completely bypassed rotational data from an Euler entirely. So you could kind of say it. If we recalc, we could say y is our look at, and start with y, and then recalculate x and whatnot. You could kind of call that an axis order. It's not. It has nothing to do with Euler rotations at this point. We've just kind of completely bypassed it entirely. The big problem with dealing with vectors is, the good thing about a vector is they're absolute. They're always right. There's nothing wrong about them. That's exactly where you told it to be in world space, is exactly what the vector is. Not like an Euler. Well, hey, I rotated it 45 degrees, but I seem to get some other value out of this. It's absolute. That's why they're used. The problem being is what we were just showing with the flipping. How do you make this thing rotate around without constantly recalculating at least two of the vectors to be able to do that? Can be problematic. Okay, and then again, which way did it rotate? If I animated my look at constraint, doing something like, let's just set that back to 1 in there. If I rotated this around in my animation in a sense, and went and animated my value, and I rotated it around to there on the other side, so it's going to be -1 and 0. Problem is, it's going straight across, and which way is it rotating essentially is happening here. So this is why things like look at constraints and orientation constraints and whatnot flip, is because this is what they're doing. They're not using an Euler, so there's no wind up of the quaternion, of the value of the rotation part of it being actually calculated. It's being calculated by vectors essentially. The holy grail of the golden flippingless spine rig. Yeah, sure, David. Yeah, something like that. Correct. Wouldn't that be nice? Okay, so what I'm going to do is I'm going to take a quick break, get a coffee, a drink of water, whatever it be, and we'll just take 5 minutes, and I'll save this out, and I'll be right back. All right, guys? Okay, so this is part 2 of Max Math 1308, and we're going to get into playing how to manipulate transforms a bit more and working with those a bit more as we get into doing other things. Can you just confirm that you can hear me okay? You can see my screen moving. I've got everything turned on all right. Just somebody let me know if that's in good stuff. Okay. So now let's start actually doing, what do we do with all these transforms, and how do they get passed on, and how do they get used by the next object and everything? And this can be really important to understand and know how to deal with. So if we actually take a hierarchy again, let's just take another box, for instance, and let's just go give it a 111 size. And I'm going to make a copy of this box up, and I'm going to send it up in Z exactly 1 unit, so they're sitting right on top of one another essentially. So we have some known values, and I'm going to link the top box to the bottom box. So the bottom box is the parent now. So if we ask for the transforms, and I can speak correctly, I'll just hide those so we can come back to them if need be. Let's set that at 0, 0, 0 for sake of argument. So if we ask for the bottom one, I'm going to call this B1, and we'll call this one B2. And so we can get at them real fast. And I'm going to say $B1.transform and have a look at the matrix that's returned. And so our matrix returned is not rotated, not scaled, no position. Which one's B1? That one, B1, yeah. And then a B2 on top. It's not rotated, not scaled, and it's 1 unit up. Okay, so it's 1 unit up. Now these two objects are parented together, and I've been telling you that basically everything's based on its parent. So you would think that, well, I move it up, then the transform of B2 should have changed. B1 has changed, certainly has moved up, and B2 also has changed. Okay, so you'd think, well, that's good. But it hasn't changed in relationship to its parent. So how do I get a transform matrix that is in relation to its parent? Okay, so what we can do is we can actually do what's called inverting a transform matrix. And if we look at a transform matrix, in terms of sort of math notation, transform matrix actually looks more like this. I'm going to go comma 0, comma 0, comma 0, comma 0. So if you were to look at a matrix, and we could even just do this, I'm going to set this number back to 1 so it looks really obvious. How should this be? I think this is actually the other way around. It should be 0, comma 1. So you're looking at x, y, z vector position, and in real mathematics, when you actually do it, you usually need to have what is called a square matrix. It means you can't have a matrix that's actually 3 across and 4 down. They need to be 4 by 4 to be able to do the math. So when you see them notated in math stuff, this is how you'll see it written out as one on top of the other. Now, a matrix can be any size. It could be 5 by 5 matrix, but to be able to do the multiplication between one to the other and be able to say, times another matrix, value and have it here, they need to be usually square. But Max only has to show you the 3 because we don't really need the other ones. We don't need that other value, but we need 4 values high, not wide. So it shows you 3, 3, 3, and 3 to be able to show you that value. So to actually invert a matrix, basically you're turning it inside out in a sense. You're flipping it flipping it over and getting the exact opposite. And so what we can do is because this is now returning us a world space value, we want to try and get the local space matrix from the parent. What we can do is we can multiply it and say, let's multiply this by the inverse, and that will invert a transform matrix of its parent. And so if we take a look what that returns now, you'll notice that it's saying it is exactly not rotated and only 1 unit up. And if I move it up higher, same thing. So what we're getting now is a local space one. If I rotate it around the parent, it'll return the same thing. Now this is strange. It's suddenly giving in this exponent value. This is actually 0. Whenever you see an e in there, that's an exponent value, and it's basically almost 0. So if we rotate that around and check, you'll notice we are getting a straight up. It hasn't essentially, this is the local space transform matrix now as opposed to the world space. Or really what I like to refer to this as, it's not local because there's no such thing as local when it comes to numbers. Locally we are where we are. When we move, we're still where we are. So this is actually parent space is what it's referred to as. So this is our parent space matrix that's being created here. And what we can do is we can actually kind of replicate a hierarchy going on here and actually play with this a little bit and play with this hierarchy and get another object. Let's take a sphere down here and call this S1. We can actually set this just like it is parented and actually create our own parenting happening with this object here. So what we've done is we've gone and returned to us we'll call it the offset TM. I like calling it. So that's the offset matrix. So this box is offset from this box this amount. And then we want to apply it to our sphere. So what I could say is I could say $S1 dot transform equals offset TM and see what happens. And what you'll notice is that there it is down there. Doesn't matter what I do with this. Doesn't matter if I rotate it. Run those two. The sphere doesn't change because we're applying this direct transform, and as soon as you apply the transform, you're applying it back into the world space. So I'm calculating what is an offset, a parent space transform matrix, but I'm placing it back onto the world space of the sphere. So it's not moving unless I go and grab our box up top here and do something and run those two. It now moves up higher. So how do I get it to be applied in the same place the blue box is? Well, what we need to do is we need to multiply it back into the space. So what this is, back out of the space. This is getting what's referred to as getting into the space of the next object. So what we've done is we've returned a transform matrix in the space of this red box. We need to get back out of that transform space now and get into do it the opposite way. So what I'm going to do is I'm just going to multiply it, instead of by the inverse, but by the object itself. So run those two now, and I actually get a sphere placed right at the pivot in the exact same location now. So if I move and rotate this and apply that, it'll place it into that correct spot again. So there's basically the ability to be able to get out of one space and back into another space. And I do this a lot when I'm calculating things and trying to get, dynamic stuff to work. Now the other thing you can do is you could always come up with an offset as well. You could always multiply in some other offset and work with it and start being able to build up other spaces and whatnot. I could say let's matrix 3 and start building in 1, 0, 0 and 0, 1, 0, and I could do let's rotate it around. We'll do, what we'll do? Just move it to start with 0, 0, 1, and we'll say multiply in along. We'll move it along x. Let's say we'll do 2, 0, 0, and we'll multiply that in to our result. So we've got it sort of being multiplied in now. And if we run that, we've got it moved along the x. So we'll see now that we can actually multiply in that value, move that up, rotate it so its x is pointing out in this direction, and then we're going to bump it out in that direction again. Get the offset. Let's apply it back in the let's apply the offset back in the space of the transform of the sphere, but that's also multiply in this transform matrix, and now we've got it offset. So what I was doing with things like the ability to be able to transfer information onto a custom rig with using marker data is that I was calculating a matrix from a bunch of points, and then I was getting an offset matrix from that matrix and storing that and multiplying it in as well, so that I could easily move this around and say, I don't want it offset by that much, I want it offset by this much, get that value, and then keep working with it. Correct, yes. So David, you're asking, you're multiplying the offset by the inverse. No, I'm not sorry, I can't speak. To get this one here, I'm taking the position, or the transform, sorry, of the child, and I'm multiplying it by the inverse of its parent to get it into world space. So this is going into to getting the local space of it, so or parent space. So that's getting the parent space of the transform. And then in this piece here, I'm having to get back into world space. So this is converting it back to world space again. So I'm taking that offset TM that's offset from this object here, and I'm going and finding out what the world space matrix needs to be for this object by multiplying it against this. So it's now placing it here, but I have to actually go and get the world space value of it, not the I guess. So it's one of those things you got to play with it, and you'll start figuring out how it all works. And then in the following line, you're multiplying it by it again. Yes, so you're multiplying it by the inverse once, and then you're applying it to flip it the other way, but not by the inverse, and you're putting it back into that space. So that's a bit of fun math to work with and start playing with, and then being able to multiply in other values. Now, if you notice, I put it first, and the order matters. It isn't. If I take it the other way and say multiply in the other direction, so it's there currently. It's now moved it over, if you notice, not lined up on X anymore. So it's no longer in this local space. It's multiplying it in after, and it's moving it across in world space. So if I said 5 and just calculate it again, you'll see that it's moving straight along the X, world space X. If I stick it in front, and run it, it's actually moving it out in the space of the parent object again. So the order of the math is very important to get it right. You can't just flip it over. It isn't like 3 times 2 or 2 times 3 adding up to the same thing. The order of the multiplication of matrices matters. B times inverse, yeah, B1 times B1 equals B2. I don't know. I'd have to play with that. No, I don't think you can do what you're talking about there. The first line isn't going to give you the correct offset TM, if that's what you're asking. You're moving something else. You're doing something else there. So this is then calculating up that transform. That's just going to throw me right off track there, David. So the order is all important. And now you can also take a look at things like working with X forms and whatnot. So if we go back, let's just work with X forms and an object. And this is again something I've sometimes heard people ask about doing things. I'm just going to go and drop in the object there and unrotate it again. And I'm going to go in and place an X form modifier on this box. And I'm going to go modifiers, and I changed it to these new. It's funny, I changed the new tear off menu system, and then when I loaded all my hotkeys and stuff, I don't have those tear off menus anymore, but all the menus are in different orders and stuff now. So something very odd has happened. I'm just going to stick an X form on there. So modifiers have a matrix as well. So if we can go and get that, I'm just going to clear this, clear all that, and let's say MTM for a modifier transform matrix, and I'm going to go get that off. What is it? I think B1 $dot B1 dot xform should return to me. Should return to me the xform modifier dot transform. Okay, unknown, but we're looking for the gizmo. So dot gizmo dot transform is getting me the transform of this right here. So the gizmo that's actually being calculated for the box. So we want to be able to actually manipulate this based on something else. Now what's interesting is if I move the object, not the gizmo, and rotate it, you'll notice that unlike the transform of an object, this is always in the space of its parent. So the objects of the transforms on an object, $transform, is always in world space. This is always in the space of its parent. So the modifier stack sits on top of this parent object, and even though I rotated it, we didn't get a rotation value on the gizmo's transform. Okay. So what we want to do is we want to actually try and get that gizmo to follow this object here. So I could actually go and say, let me just unrotate that and just make sure that it is currently unrotated. And let's just move it down somewhere. Let's actually just position it down again there and just move it out. So move that down. There we go. Should be able to see what's going on. So now we want to be able to do is manipulate the transform of the gizmo and start playing with it and doing something with it. So there's the transform of it. If I just go and take that transform value and apply the transform, so equals $, what did I call it? S1 dot transform. You'll notice that the gizmo is popped over. The box is over here still. And move it up. All's good. It pops the box over into this place, and it's actually not moving the box. You can see the pivot of the box is staying put. Rotate it over 45 degrees. Looks good. Let's go and take the box now. And it's interesting. it's not popping over to the sphere anymore because the box is no longer at the origin at 0, 0, 0. And if I rotate that box, it's just staying put. It's because we're getting the transform of this object sitting in world space, and we're applying it to this gizmo sitting in the space of that object, and we're not getting what we'd expect again. So what you could do is you could go and find out what space to get out of or into again. So let's try a couple things. Let's actually just go and get out of and it pops over there now. Let's try the inverse. Bam. So we can actually think about what we're doing is we've got our box. Our box sits over here. Okay, it's actually sitting over in this location here. We can prove that by turning off the gizmo, just turning off the X form. So there's the box all rotated over. What we're doing is we're getting the transform of our sphere. We're getting the offset transform, essentially multiplying it by the inverse of the box to get that offset transform. And we're applying that back to the gizmo of the X form. So the X form now follows the sphere. So anywhere that sphere rotates, moves and rotates to, we'll apply that to it, and it'll actually set up onto it, and it'll apply it onto it. So the transforms can be multiplied back and forth. You just need to play with them sometimes to figure out how to get into the space of one, and then how to get it back into the space of something else. And you can work with them and create basically your own hierarchies. So if you needed a gizmo to follow some other object in a scene that's a modifier, you can do it just this way and be able to go and get its values correctly. So does that make sense, guys? Transforming in and out of spaces. Everybody else good? Can I clarify anything? Is this new, Kevin? I think you guys have done some of this. Yeah, you're good, Valmore, or yeah, it's new? Oh, good. I figure it's new for you guys and it's going well because you guys already had me for, what, a couple of years there or whatever, some time ago. So now let's take a look at playing with vectors a bit more and calculating curves. Let me just see what I have to cover again. Let's normalize matrix values, cross products, Bezier curves, dot product. I want to get into array casting and barycentric coordinates, so I want to discuss those. So how much time do I have right now? I'm doing pretty good. Okay, so let's take a look at a Bezier curve and how this is calculated. This is actually on my website. A little bit of information about it anyways. And Bezier curves are something I dug and dug and dug, and I finally found this really cool animated graphic one day, and I went, what? That's it? Because unfortunately you go to a lot of the math sites, and I'm not a mathematician by any stretch. I'm not good at math when it really comes down to really pure crazy math and reading all the math notation stuff. I don't have a clue what it means. And so I was digging around, and I suddenly found this great example of how to do a Bezier curve, and went, oh my God, that's it. That's all it actually is. And as it turns out, it's actually a recursive function. So it's a function that calls itself over and over again. And the basis is this very simple bit of mathematics right here. This simple bit of math is just simply saying, well, we're going to create a curve. And in this case, we're creating a curve between these 2 points. And it's going to be a straight curve. So essentially no Bezier handles. Because if you think of a straight curve with a Bezier handle on each end, you actually have 4 points, not 2 points. Okay, so this is a 2-point Bezier curve. And the way a 2-point Bezier curve works is we're actually going to find a position on a curve at any point in time. And again, we think of time as an animation timeline, so at frame 20. Well, that isn't necessarily the case. Time is referred to in mathematics as a point along something. Okay, and in this case, what we're looking at is a point along a curve. And so that time is going to be represented by Q1 in this case here. So this point here. And what we're doing is we're getting that point in time. And you notice I've got T in here. So we're going to do a little bit of math that we've already done. We're going to take, in this case, it's funny, I wrote this down wrong and put these wrong. Most arrays are all 0 based, so this should be P0 and this should be P1. So we're going to take the endpoint. So you can think of this, if you're looking at these two, we can think of P2 minus P1 times the time. So a normalized time from 0 to 1, no matter how far away these are from each other, but a time from 0 to 1. And then plus the first point again, so P1 again. So add it back in again. So let's actually make this work, and then we'll start making it into a full-blown curve and take a look at actually building a curve from this. So I'm just going to go and hide that off. And we're going to take two spheres. And I'm just going to call this again. And we got to be careful because we got a bunch of P1s and stuff. You know what? I'm going to go and just do a reset. I did this last time. I think I did this class, and it caused problems. I had all these P1 objects, and I was calculating them, and nothing was changing. So there's one point, and we're going to call this P1. And we'll pull this point out here, and we'll call this P2. And we'll just create a box. And we'll just make this for sake argument 1, 1, 1, and we'll call this Q1. And what we're going to do is we're going to make this real time so we can actually see it happen. So let's actually go and set a position script on here. Let's calculate our position script and work with it. So what we're going to need then is we're going to need a P1, and we're going to need a P2. And I'm going to grab my P1 node, and I'm going to say assign constant. And I'm going to grab my P2 node, assign constant, and assign those two in there. So there, we've got the just two nodes as opposed to their position controllers or anything, but they're actual nodes. So let's start writing the math then. So this is pretty straight up. P1 minus P0 times time plus P0. So let's work that out. So let's go and do P1 dot pause. We'll just do dot pause. We know everything's in because it's usually when you've got things like constraints on objects that P1 dot pause wouldn't return the correct value. You would need to go through the transform. Sorry, P2 dot pause minus P1 dot pause. And if we evaluate that, we'll end up with this object that's way over here somewhere, doing some wackiness. And then we'll call it times time. And time is going to be a value from 0 to 1 somewhere in between. So let's just go 0.5. Try that out, and you'll notice it's doing something else a bit weird. And then we want to add in plus, what is it, P1 dot pause, and add the position of value of the first one back in. So once we've done that, what we've got now is a box that stays halfway between. This is kind of really acting like a position constraint, 50-50 in between. If we change the value to 1, it'll skip all the way over to the, oops, I just did 0.1. I did 1. It'll jump all the way to one end. If I change the time to 0, it'll jump all the way over to the other end, and now it's somewhere in between. So let's actually set time to something as well. Now we can't use t. I'm just going to call it the time. And we're going to call this the time. And I'm going to say create. And let's just go and grab another object for sake of argument here. I'm just going to grab another little box. We may have done this at really small scale, but you'll see where I'm going in a second. And I want to say the time, just throw this as a constant. And the time dot pause dot will go along x for the fun of it. So what I'm doing is I'm using the dot x. Why aren't you working? Pause.x. Oh, man, there we go. So what I'm actually using is I'm using the position of this object along its x now from 0 to 1 to be able to calculate it moving through that along that line, so along that path. So we can actually just animate this moving along that line as well. Let's just animate this over 100 frames. I'm going to turn on animate. I'm going to move this moving from 0 to 1 for the sake of argument. So now if I actually scrub my timeline, my box is actually moving between 0 and 1. And let's just follow the function curve as this starts to build. And so I'm going to go into in here and turn on trajectory. And we can see what's happening now. I'll move that down there and that down there. And you can see what it's doing is it's actually calculating from one to the other and coming up with a new position. So this is calculating Q1 at this point. So let's make a 3-point Bezier curve now. I'm going to call this P3. And we need a new box. I'm just going to move that over and I just copied it, so it's sitting right in the same place obviously right now. This is for the first box. This is for the first one. Let's call this Q2 now. And in Q2 I'm going to have a controller on it as well, and I'm just going to call this P3, create, assign constant. And let's change the math up a little bit. I'm going to call this P3 and P2 and just move them all over one and evaluate. So now what I've got is I've got two boxes that are scrubbing between those 2 points. You say, well, Paul, that still doesn't look like much of a curve. So let's take another object, and this time let's take, just make it real obvious. We'll do, I'll just do a circle. We'll call this C1. And I'm going to take the math right off of this one. So I'm just going to, just to make my life easier, I'm going to go and say copy. And I'm going to place that right onto this one here with a paste copy. So it's going to be sitting right exactly where this first one is now. Pop open its properties. And I'm going to say there's a Q1 now and a Q2. And I'm going to set Q1 to be the constant. And I'm going to set Q2 over here to be a constant. You guys are probably seeing where I'm going now. Oops. And I want to change up the math. And I'm going to say Q2 between Q1 and Q1 and calculate it. And let's, on this one now, go into our object properties and turn on trajectory. And let's have a look at the actual trajectory that's being created. So now what I've got is a Bezier curve being generated with 3 points. So it would be like having, you could call it, in spline terms, maybe this point is, linked up to this one as far as Bezier handle goes. So this is the Bezier handle of this point. There's no Bezier handle on this one. So there is an actual, the way a Bezier curve is generated and can be calculated. Is that new to anybody? Has anybody seen that done before? It can be actually pretty cool. I've used this several times, and I actually used to calculate until they sped it up. Splines used to be really slow in Max, and this now actually is, it works quite quickly, believe it or not. Even though it's using Maxscript, what I did is I wrote a recursive function that no matter how many points you sent it, instead of making all these nodes, it doesn't have to do that. Basically, you send it the 3 nodes, and it says, calculate a midpoint. Calculate a midpoint. Take that new point, and that new point, calculate a midpoint. And it doesn't matter how many you send it, it recurses through until it's run out of points, and it recalculates it. Now, the problem with this being is it can get very, very slow. And it can get really nasty slow as you add more and more and more and more points. You have 20 points. You think about how many recursive steps have to take place. For the first 20 points, you have to calculate 19 subpoints. From those 19 subpoints, you calculate 18 subpoints, and 17 subpoints, and you go all the way through until you're down to 1 point, and you've got that final value that's calculated. So doing a Bezier curve, this is called a quadratic curve, by the way, can get very, very slow the more points there are, and it's, it increases exponentially as it goes up, and it can become very, very slow and cumbersome. So a Bezier curve is quite interesting, and I discuss it on my site. We're not going to have time to get into it today, but doing a Bezier curve can be quite interesting, and I think if I pull up my website real quick, I'm just doing it off on the other screen here until I find it. Tutorials. There it is, Bezier curves. The way it actually works is that I'm calculating the points. Just use my pen drawing here. So I'm calculating all these points. This one inside here is actually the quadratic curve between all of those. It's getting exponentially slower. This one that's flowing through is actually calculating quadratics only using 4 points. So it's actually making some invisible ones. When you view this on my site, there's actually a point projected out from each one of these as like Bezier handles that it's using. So in between any 2 points, it's calculating 4 points to come up with a placement. And it's going through and looping through all these points, but any time, as soon as it gets out of this quadrant, we'll call it, it calculates another quadrant. So it's only ever having to calculate 4 points based on a time value that's being passed through it. So it's actually taking them all and figuring out its time values in between each section. And working them out. So it's only ever having to calculate 4 points at any given point in time. So it never gets slower doing it this way. If you do it as a one big quadratic all the way through, it exponentially gets slower and slower and slower as it has to calculate through and get pretty nasty pretty quick as far as speed goes for each one. So that's kind of fun to play with as well, and can be important in understanding how to do some things. Again, the math can be quite important. So I've used quadratics like this and calculating Beziers to control other things and to find controls for blending in and out of stuff. Oh, it is? Oh, that's right. This is the one that stops or something halfway, right? I'll have to try and fix that. Remind me again. I don't know why it does. Hopefully I still have it. If not, I'll just have to do another recording of it if I still have a file. So I've often used this just calculating behind the scenes a point in space between things. It could just be for calculating or ramping in and out color values or something, and applying the value, the final position in between the two is coming up with a value. So you can use it as a way to calculate point between two, a 0 to 1, and then what's its actual y value up and down between those, is going between them and whatnot. Things of that nature. So, there's all kinds of fun stuff you can do with Beziers that can help you a lot as you start getting sort of deeper into things. So that's how you calculate those. And again, it's all on my site there, so you can take a look at it. But that's a good explanation of it, I hope. So was that new for anybody? Kind of new? Anybody else? Yeah, it helps to actually go through making it, Kevin, to actually play around with the mathematics and see it working. I mean, I'm being more of a really came from the artist side. Um, it helps me to see the math as opposed to looking at raw mathematics, which makes my head spin. I need to sit down there and play it out and see what happens when I do different things. When I play with this, back and forth. Animate's not on, so it looks like it's moving the entire curve. You can actually project it further than it's supposed to go as well, which is kind of fun. Projecting it past the value 1 can actually extend it off. And seeing what happens there, you can shoot it off into space, basically outside of either end of the curve, and come up with all kinds of really fun stuff and start playing with it. Yes, I'm calculating it multiple times, though. That's exactly what I'm doing, David. I'm calculating an equation that defines a straight curve, and then I'm using it multiple times to calculate the final one. And again, it worked quite well. There's other ways of doing it. I've never gone and sorted them out. And there's all kinds of other simplified math, like Hermite curves and whatnot, which will give you simplified mathematics. It's much faster, but you don't have as much control over the curve and the end result of the curve as the final product does. So let's start looking at other things. We're going to start shooting some rays. We're going to start calculating some surfaces, sticking objects to surfaces and whatnot, and taking a look at barycentric coordinates. My throat's starting to dry up, so let's take another break right now because another hour has gone by, believe it or not. I'll just do a save down, and then we'll start again in 5 minutes. All right, guys? Sure deal. Okay, part 3 of Max Math, MC 1308. I just condensed this down just for the fun of it, and essentially creating Q1 and Q2 just as variables inside the script controller, so that I no longer have objects being calculated, but we still have the quadratic happening here. So this is giving us the same result basically, and playing around with it. So there is the simplified, instead of having multiple script controllers going to be able to do it. So let's also get into dot products now. What a dot product is. And dot product I use all the time as well, and it can be really, really handy for all kinds of lovely stuff. So let's just do a reset again, and I'll just pull up. So we'll go with some boxes again, and we'll do and we'll get back to just 0 positions here. Okay, so the dot product, dot of a vector, is an interesting one to start playing with and figuring out what it does. I'm going to have 2 boxes actually. And what it'll do is we can actually use it to calculate angles and get the angles between vectors and the like. So let's actually just keep using this because it's been working quite well for us. And I'm going to call this B1 again, and this one B2. And let's go and get the dot product. So the dot product is simply dot. And what the dot product requires is 2 vectors to be passed to it. And those vectors, in this case, we're actually going to use the x vector of the matrix of each of these to be able to get the dot product between these. So I'm going to go $B1 dot transform, and you can get to the different vector values in a transform a couple of different ways. You can just sort of look at them as an array, or you can use a little bit longer form, which might be a little bit redundant either way. Row 1 in this case will return to you the vector from the first one. And so I'm also going to go and get the vector from the second one, second box, and just make this a little bit more visible. And we're going to clear it, and I'm going to ask for the value. We get a value of 1. And so what it's telling me is that both vectors are actually pointing in the same direction. So let's do, I've got angle snap on. I'm going to rotate my second one here. I don't have angle snap on. Now I do. I'm going to rotate it around 90 degrees. If we look at the local axis of these, our vector is now pointing at 90 degrees to each other, and run this. I'm going to get a value of 0. I'm going to continue the rotation around another 90 degrees, and now they're pointing actually in two different directions. I'm going to run it again. We get a negative 1. Rotate it around another 90 degrees. Rotate it again. I get 0 again. And then back to its starting point, really. We get a value of 1 again. So if the two vectors point in the same direction, what we're getting is we're getting a value of 1. If they're pointing perpendicular to each other, we get a value of 0 in both directions. If they're pointing in opposite directions, we get a value of negative 1. So what can this be used for, and what can you do with it? Well, if you want to try and find out whether or not an object is rotating, let's say, or what the angle is between two objects, we can actually use the dot product. And so we'll call this just D for dot product, just to make sure we don't get too long here. And we can say the arc cosine, what is it in, is it arc? Acos, thank you. The arc cosine of D of the dot product is actually going to return the angle between them. So right now they're back to pointing in the same direction again. Let's actually, I should have animated it the first time, but I'm just going to go to frame 10. Just going to turn on animate, go to rotate, and I'm just going to rotate it around 90, 90 at 20, and then 90 at 30. And what we can do is we can check and see what that value is going to be at any given point in time. So we can rotate it around, and we're going to get a value of 90. So the 0 degree value, if I go to the other 0 degree value, which is over here, and run it again, I'm going to get 90 again. So we know they're 90 degrees to each other. The interesting thing is we didn't get positive 90 and negative 90. We got 90. So we know they're 90 degrees to each other, but we don't know which way they're 90 degrees to each other. If we put it halfway, we get 180. So we know if they're pointing opposite ways. We know if it's 0 degrees, we're pointing directly at it. We know that if it's pointing away from it, it's the opposite way, but we don't know 90. It can go either way at 90. And we don't get negative 180. So how on earth do we get negative 180, and how do we calculate this and find this value out? And the reason why we can use this is a couple places I've used it, is for calculating whether or not an object should be pointing at something, essentially, and making a target, a look-at target, building a transform matrix for itself, for all intents and purposes. Let's take a new object here. Let's turn on animate again. Go along to frame 20. I'm going to move it straight out, and let's go out to 40, and let's angle this, and let's just show the trajectory real quick. So there's the trajectory for the object, and we could throw these all in a smooth tangent just to make them really nice and clean, I guess, as well. And so we see this nice smooth tangent going here. Now what we want to do is we want to rotate this box so that we actually can rotate it and point down its direction of travel all the time, so that we can actually point it to where it's supposed to be going, and have that automatically happen. Now I've used this in particle systems because I don't know, maybe there is now, but I haven't looked, but I had to do flocking birds, flying from basically target to target years ago when pflow first came out. And of course the birds were great. I could get them to go from target to target. I could get them to look in the direction of their target as well with pflow, but I couldn't get them to angle and tilt as they turned corners properly, and so I was able to use this method. So we're just going to get it to, in this case, just to point down its direction of travel and find out where it is. Now the thing is what we don't have is we don't have two vectors, because we're going to use itself here, whereas over here we were using two boxes. we're just going to use itself now. So to get the two vectors, what we need to know is really points in time. We need to know where it's been and where it's going to be able to get some of this information. So we can actually get this information from points in time. So we can say, well, let's compare where it was at 1, or frame 0, and frame 1. And let's figure out where we're going here and where we should be angling. And let's take that all the way down through time and sort that out. So let's go with a script controller again, and we're just going to rotate it around the Z to keep this nice and simple. So I'm going to go down to the Z rotation, assign controller, and we're going to go with a float script. And we can just assign itself basically. So I'm going to go, hopefully this works, we're going to go B1 create and constant. Let's see if it, now it's going to give me a circular dependency. So let's actually go with another point. We won't animate this one then. We're going to animate an object on top of it. So I'm just going to make a copy. And we are going to go and do, it's not an instance of copy. And let's just make that larger, I guess. We'll do that so we can see where it's going. And so it's going to be parented. Let's kill all the keys on it. And let's just go in and should be able to get its parent to work in there. So it's moving along with its parents. So let's go and put it on this one now. This should work. Assign controller, float script. We're going to call this B1 again. And that's going to be this object down here. We may have to go with a controller. Yeah, there we go. We could have gone with a controller on itself. Its position controller would have worked as well. But I want to trying to keep it simple here. So right now it's not rotating, it's not doing anything, it's just going to keep doing what it's doing. What we want to do is we want to be able to rotate it and pump a value into the rotation. So let's start building this up. We're going to use a couple of values. P1 equals B1.pause, and we're going to go P2 equals at time. And we have an interesting couple of things we can pump out here. T will always return time, and it's a constant value. And it'll return time, or we can return frames, and we can get those frames. So we're going to say at time F. At time F, and we're actually going to, you know what we're going to do? We're going to look backwards on this one. This might make more sense. We're going to look backwards on this one. Oops. Time F minus 1. So we're going to look back a frame on the first one. So we're going to say at time, frame 0 when we start out, back one frame, -1, get me the position of the object. You're going to find it's probably going to do something really wacky to start with too. And then the second one, we're just going to go ahead and say, give me the position. So what we're getting now, so let's just print these. Oh, come on. Well, Butterfingers trying to teach and type at the same time. I'm going to say, let's go format P1 and P2 and P1, P2. System exception, parsing error. Oh, I've never tried a format in there. I wonder if it's not going to like it. Oh, dot pause. Dot pause. I don't know if it's going to like it. P1. No, those are position values. Let's just use print. How's that? I've never tried a format in there. Print P1. Print P2. So now we get a whole bunch of printing back. And so we're getting a bunch of values. So if I actually scrub forward one frame and just clear that, pop forward a frame, you'll notice that we're getting two different position values. So every pair of position values, the first one is slightly behind and giving us the position prior to the second one. So essentially what we're getting is at frame 1, let's say, so back at this position here, we're getting a vector at the start and a vector at the end. Well, what we can do now is we can actually make a target out of this. So we can go ahead and target from one to the other. So let's go and say, we'll say dir, direction, equals P2 minus P1. So what we're getting out of that now, and when we evaluate it, and let's just print that, print dir, what we're getting is a direction vector, and so it's a vector. Now it's not a normalized vector at this point. It is a direction vector. So a direction vector isn't normalized. Now when you're using dot product, you really want those vectors to be normalized. You're going to get wacky results from them. Okay, so at this point we're getting this direction vector, which actually is telling us which direction we're pointing in. And if we were to apply that value back to another object, it would be circling around the center point here, pointing in the direction, and giving us magnitude as well. So from this right now we can get we're actually checking the length of this vector would give us how fast we're actually traveling as well. So between each frame we can know how fast have we actually gone, how far have we traveled between that in a straight line. So there's our direction vector. Let's normalize it, and we'll just say normalize and get that value, and now that value is telling us which direction we're actually heading in. Now, what we need then is we need some key point to start with. We need some point to come off of, and we'll just use this as the starting point sort of for our our world point. It's just going to be a standard 1 0, 0 now, because we're all lined up. So I'm doing this really simply. So this is our starting point. So with our dot product, we needed the two vectors. So what I'm using is one that's just aligned to world, and now one of them I'm getting by basically moving the object and calculating where it's pointing and which direction it's traveling in. So I could get the dot product of these two. I'll just say D equals, and we'll go dot dir, and we'll just go print D. And if I check that now, I'm going to be getting values that are going to be changing. So those are the angle values that can now be turned into angles as we go. So let's actually go and get the angle of that. So we're going to say A equals A cos D. And if I scrub now, oops, and if I print it, it might help. I'm going to say print A. So here's the angle change that's happening as we're traveling along. I'll just get rid of these entirely. So there's the angle change that's actually happening. And so I could actually apply that angle back to our object and just say, let's just return A now, and that should be our angle. And you can see that it's kind of jumping around by the looks of it, doing some freaking out. Actually, I'm not quite sure why it's jumping around as much as it is, to be honest with you. I'm not sure why it is doing that. A cos as Euler. No, it doesn't matter. It's just returning an angle at this point. So we should be able to get an angle change. Let's actually just do something for a test and see what's happening here. I'm going to go and grab all of those and just set them to straight up angle changes. And for some reason it's giving me not what I expect. Here, I'm going to call you a liar. This should be easy. 64. So why is it going? You think so? Oh, you know what? Yeah, you're right. And we're going into, yeah, you're right. Deg to rad or rad to deg. There we go. You were absolutely right. Thank you. Rotations in Max, so this is when you teach and you forget what you're doing. Basically everything's radians, and when you calculate an angle, you have to apply it as a radian because it's sort of the pure form of rotations angles, right? So we're going to get into this. You can see it now rotating in the direction of travel. So it's going to be messing up to start with a bit as it gets started and starts calculating. But then it starts curving nicely. Now it's messing up because we don't know which way. If you notice as we start off, that angle's tilting the wrong way. It's rotating. The very first frame can be wrong, but then it's tilting the wrong way, and then it's coming back and tilting. So we're going to have a problem when we get to the down here that if we pulled it out again, let's turn on animate, that as it starts calculating the other way, it might start freaking out again as well. We don't necessarily know which way we're turning. That's our problem. We're going the wrong directions is what it boils down to sometimes. So let's now take this and calculate going down here. Oh, come on. I'm trying to get it to scale in that little space. And just set them all smooth again. And so you can see it calculating and turning the wrong way again. That's because we actually don't know which way we're going. We don't know, we're not getting a right and left angle. We're getting an angle change, and that angle is always positive. So how on earth do we get a negative value and know that we're going the opposite direction? Well, what we can do is we can actually calculate and look at another vector. And we can say, well, what if we actually compared our direction vector against a perpendicular vector that went from 0. So I shouldn't have deleted those objects, but if our vectors are perpendicular, so if we're starting off with our direction, but we're looking at and comparing it to one that points perpendicular, that value is always going to return 0 when they're in this this way. Now, if it starts actually going away from it again, because this way would be 1, this is going to be a positive number, this is going to be a negative number, going the opposite way on it. So what we can do is we can actually, hey, I didn't know I could right click and do that. That's kind of cool. I don't think I got out of my pen. Oh, I even went back to the normal pen. Good. So then what it's going to do is we're going to find that opposite one, and we're going to find out what we should multiply it by to go the other direction, or at least a positive negative value. So we're just going to call this something like m equals, and we're going to ask for the dot product again, this time of our dir, and one that's perpendicular, so one that's actually pointing in the perpendicular, 0, 1, 0. And this m now, if we print m down here, we'll be returning a positive and negative value. So you can see that it's actually going up and down in positive negative fashion compared to where it's supposed to be going. So what we can do now is we can actually use this, either you could use it as a multiplier, which is kind of cool, use it as a multiplier for things, for the amount of rotation you're going to apply for something. But what we can do is we can say if m is greater than 0, then a, else negative a. And what we should have now is our object pointing and traveling the direction that it's supposed to be. So the dot product can be used to calculate that angle as well, whether you're going positive or negative. You can avoid the if doing what? Tell me, David, because I'm too busy trying to teach to think about better solutions. Yeah. Okay. Yeah. So no, that's good. Another good solution. And right now at the ends, you'll see it freak out, and it does a little, skip and jump at the ends. Now what I've got is something that works really well here. Wheel rotation. And so what I'm doing is I'm doing some wheel rotation math, and I'll show you how I've gone and calculated this. It's actually using every frame, and it's automatically calculating itself going around. So we could have used, as we turned, we could have actually calculated its values. Now I'm rotating this itself. We could have moved the wheel around and let its rotation be taken care of by itself by what we just did. Now the next little bit of math we're just going to look at is an interesting way to go about actually calculating and working with rotations of a wheel. One of the things people try and do is they set up a wheel like this, and they set up a little bit of math, and they can move the wheel back and forward along X, and it works. They rotate the object around its Z-axis, and they point it off perpendicular to where it started, and the wheel no longer rotates. That's because everything's relative to its parent. So at that point, you're not actually moving along the X anymore, you're moving along the Y. So then you try and calculate in those, and basically you can go forward and backwards along the Y now. And then you need to go up a hill. Well, if you're going up a steep hill, you're going up Z, so it's no longer rotating anymore. So you can see where the problems start coming in. And then as you start driving around in circles, you run into the problem that as you drive forward, it rotates forward along X, then it rotates forward along Y, and then it starts going the other direction, and it starts rotating backwards because we're now going negative along X. So that's not going to work, and you're probably going to get a pop somewhere in between the rotation from one to the other. So I don't do rotations of wheels in cars that way. I do them as a rotation value that is actually being calculated by time again. And so let's just take a look at what I've got. I've got a script controller sitting on the Z, and that's the entire explanation of what I'm going to tell you. There it is there. Well, that's no good because it doesn't actually do anything at all. What I've done is a nice neat little cheat. I could have written it all out in here, but it's going to run into two problems. One, I need some values that will hang around in the scene over time. A script controller is calculated every frame, and anything inside of the expression is being recalculated. I need to be able to store last values. What did I last calculate to be able to do what I'm about to show you? And so what I'm doing right now is I actually have a custom attribute definition. So you can see this custom attribute definition. And typically people put that in through, I don't even know how you get into it through this new menu. I should have flicked it back. The attribute editor, I don't even know where it is in this thing now. Editors, motion editors, sound, relationships, attributes. There you go. Attribute holder, attribute editor, parameter editor. This will throw it onto certain things, but not necessarily everything. You can actually stuff a custom attribute definition right onto a controller if you target the controller as opposed to targeting an object, because this in itself is a max object. So let me just go and get that and show you what it looks like. I'm just going to go and grab my manage attributes, and sorry, just spinning up my drive here as it loads up that script. Yes, I use this for my car plugin basically. So here's the definition that is actually on the actual, so this custom attribute definition has been applied right onto this controller. So when we look at that, what we have is this simple little definition here, attributes, wheel def. Actually, the redefine's still in there. It doesn't need to be there essentially. And what I've done is I've then set a couple of variables, and these are those variables that need to be used for the last thing I calculated. So what did I calculate last frame so that I can use them again in this new frame? And here's the reason why. I'm going to be calculating the angle of change of the wheel over time as opposed to the absolute rotation value. So what I'm going to do is I'm going to calculate between frames 0 and 1, how far did the car travel, what's that angle that needs to be applied to the rotation, and apply it. The next frame, I'm going to calculate the angle of rotation between frames 1 and 2 and apply it. Now, if I just apply it, what you'd find is the wheel would sort of like jostle back and forward and not keep rotating over and over and over again. It would just rock back and forth because you're applying this angle. What I need to know was, what was the last angle that I calculated? Calculate the new angle of change, add it to the last angle, set that to the value of the rotation, and then make last angle equal to the value again. So what I'm going to do is do all the work inside this custom attribute definition with a function applied to it. This works really nicely as you start calling it, because you also don't need all of this stuck inside this horrible little script window here that isn't color coded, doesn't automatically indent for you, doesn't do all kinds of stuff. You know, it doesn't do code completion for you or anything like that. So you can write it all inside a custom attribute definition and then just keep updating the definition until you've got what you're looking at. So the way this works then is I've got these two local, and the way you get at it is that, first off, is that this is a key word in script controllers that returns an instance of itself. So this will actually return this script controller. Because my wheelDef attribute is applied to this .wheelDef will get access directly into the attribute definition. This .wheelDef.rotateWheel can call the function inside of my definition. And then I'm passing it a couple of different values at this point. This code is saved in the wheel object itself. Yes, it's the script controller, David, is actually on the Z rotation of the wheel, and the custom attribute definition is actually on the script controller, so it's all saved in the file. Nothing needs to be run outside of it. It's all contained inside of the file and inside the object, basically. So what I'm going to do is I have a couple of objects that I've got predefined here. One is hub, and hub is the hub of the wheel. So just like we were sort of doing before, I had this center point that was moving, and that's this one here. And then rad.value is actually the radius of our cylinder here. So we're actually tying into that actual radius value and grabbing that radius. So it doesn't matter what the radius changes to, the rotation on the wheel will actually remain correct because I'm calculating it as it's supposed to be. I can even change its height, I guess, based on the radius, so it sticks to the floor. So it doesn't matter how big I make that radius, the wheel rotation will correspond directly to what is needed depending on that radius change. So I'm making sure I'm piping that into it as well. So I'm passing those two things into a function here. So there's our function, wheel rotate, that I call. Pass it in the hub, pass it in the radius. So I pass those two things in. There's the wheel hub and radius. And one of the things you need to do, which is a bit of a, this is where the problem comes, you kind of need to bake the solution. Watch what happens here. I'm just going to go along to frame 50, and I'm just going to click on it. Objects rotated. Watch what happens as I rotate backwards now. As it rotates backwards through this, it's going to suddenly get to frame 1. Watch what happens at frame 0 as it pops. And it suddenly pops. Well, the problem with just clicking forward in time here is it hasn't calculated every frame, so the actual rotation isn't correct right now. It needs to actually skip through frame by frame to be able to get there. So you really need to bake this before you send it to a render farm or anything. You could render it frame by frame, but you couldn't start one render on one box from frame 0 to 10 and the next one from 10 to 20 because the rotation on the second render wouldn't be correct to start with, and the wheel would pop. So we're sending it in. And what we're going to do is, the first we're going to do is we're going to do a little, yeah, you could point cache it or whatever, David, as he points out. I just create a baking function as well that bakes it all down to keys in a list controller and turns off the script controller, basically, weights it to 0. So what it does, it says here, is current time is a command in Maxscript that allows you to get the frame that you're currently at. And it says if we're 0, then reset our last angle and our last position values back off to the defaults so that we're defaulted back out. So it's defaulting the angle to 0, and the last position is defaulting to the wheel hub its position. So where are we currently? And just start that as the start position. So we're going to do some of the same thing. We're going to get a distance command, and a distance command can work on two things. It can work on position values or actually objects directly. And in this case, I'm taking the position. So I'm saying the last position that I stored and the wheel hub.transform.position. So where are you now currently? And get me the distance traveled. At frame 0, that would be nothing. At frame 1, it would be the distance traveled. Because we need to know how much we're going to rotate it based on that. Then we're going to calculate the direction of travel forward and backwards, because this is something we're going to need, because we're going to need that because we need to know how have we gone forward or backwards. The problem with this solution is, unlike the solution that I was talking about before, where you're using the direct X, Y, and Z values, is when the car keeps going around in a circle, it'll keep rotating forward perfectly fine because it's traveling forward. But when you move backwards, it actually doesn't know that it's moved backwards. It basically says, hey, you've moved a distance. You've moved X distance forward, therefore rotate it forward this amount. And so the rotation's wrong. So now we need a multiplier to say, did you rotate forward or backwards? So we're going to use that dot product trick. So I'm creating a direction, normalized direction between the last position and the current position for a little direction vector where we currently are. I'm going to take the and multiply a multiplier values in the dot product of the direction vector and the current wheel's hub. So I'm rotating it myself here. So I'm rotating it. So I'm looking at the X rotation value, the X vector sticking out. And I think in the wheel it's pointing forwards. The X vector is pointing forward. So I'm getting that idea of now whether or not we're going forward or backwards. Because if the wheel's pointing forward, way over here, the X is pointing forward and I scrub backwards, well, now in fact the vector that we're direction traveling in is pointing the opposite direction. So we actually have a negative value to be able to calculate that. So now what I'm going to do is I'm going to set the last position to the current position for the next frame. So now the next thing I need to do is just reset this. So I've used it. I've calculated and used my last position as many times as I need it. I'm going to reset it so that it's there waiting for the next frame calculation, and I'll recalculate that again. So reset that position value, and then start doing a little bit of the fun math. Of course, circumference pretty easy to find on the web somewhere. 2 pi r, so 2 times pi times the radius. So we had that radius, that rad value being passed in. And then we need to know the angle per unit travel. So how much do we need to rotate per unit traveled? So we're going to take the circumference that we've calculated and divide that by pi times 2. And that will get us the degrees that we need to actually rotate forward and put that in there. So what I'm doing then is just simply using an if statement again, and maybe David's would work better or whatever, or faster or slower, it doesn't really matter. The if statement is basically saying if our multiplier is greater than 0, then go ahead and add it. So take our last angle and the plus equals, add it on, and add it on to the so the distance traveled divided by the degrees, add it on. If it's not, or sorry, subtract it from it. If it's not, add it on to it. So basically we can say add or subtract that rotation as we need, and we get it. I just found my solution can end up with dividing by 0. Oh yeah, there you go. So the this is just simply calculating the angle needed, and it's adding it on to whatever the last angle is, and then basically calculating whether or not it's moving forward or backwards. So pretty simple custom attribute, and a simple way of being able to work with some math that needs to be able to store a last value, is being able to use those custom attribute definitions applied and directly put onto something. Now it could be applied to a couple of different things. You could apply it to an object in the rig, directly on the object. You could put it onto a modifier. You could do it something like that. If you look at my car rig that's on my site, it has a bit of a different solution. And let me just go pop back to it here quickly. So this is my my car rig that's in here, and I don't know if it'll play for you guys, but you're only animating, in this case, you're only animating the position of the truck. You don't rotate it at all, and the direction of travel of the truck and the direction of travel of the steering, the rotation of the wheels, and everything's all being calculated for free, plus the suspension and everything's all being calculated. And if you look at the whole system, the way it works on the car, there's actually this custom attribute definition that's been applied to an attribute modifier. Or sorry, I think it's a scripted plugin modifier. And essentially all of the math, all of the code, all of the functions are all housed inside of this one big, again, you could do it through a custom attribute definition if you wanted. It's housed all in there. And then all of these script controllers that are on all the different parts, like the wheels and everything else, are all referencing that attribute definition. So when it calls it, it says, how far does this wheel need to rotate? Pass a wheel rotation function, a couple of things, get the return back and pump it back into it. So it works really well. How much miles per gallon does your car make? Who knows? Infinite. So you can actually use that sort of idea to encase into it a whole lot of code that's way easier to read. So if you got a code-heavy rig, like a car rig is, don't be putting all that code into individual script controllers. It can get nasty trying to manage it, because you suddenly realize, hey, shoot, my wheel rotation code is wrong. Well, you have to go change it in 4 different wheels now. Instead, if you have your function in one place in this custom attribute definition, you can go and make changes to it, and all 4 wheels just got all the solutions corrected for it and updated on it. So it can be a very clean way of handling your math and handling all your bits and pieces, so that it's a much cleaner way of just managing everything going on. I'll often do it with character rigs, even, where I'll have if I've got functions for doing like mirroring sides of character and stuff and whatnot, it's contained in a part of the rig, so it knows what it is. It knows where go and get that information from. So there is doing some wheel rotations and whatnot. Now quickly I'm going to work on and show you guys some hit detection, and then we'll call it a day, because my throat's getting really sore from all this talking. I think I'd be used to it from teaching and whatnot. I'm just going to say restart, or reset, sorry. And I'm going to say clear that and that. And we're going to take a plane. And I'm going to take just a point helper. Helpers, I said helpers, point. And I'm going to move it up above our plane. It's an ugly color to try and look at. That might be better. I'm going to rotate this over so the Z is pointing down. And I'm going to go and take another point helper. Oops, I said another point helper. And I'm going to set that right there, wherever it might be. What we're going to do is we're going to place this point on this surface using this one as a laser beam, essentially, and take a look at actually calculating that. Now, what we can do is we're just going to do that real manually. This can be put into a script controller, but we're going to use intersect ray EX and discuss rays and ray values and whatnot. So what a ray value is, if you type ray, you'll actually get a ray value. A ray value is, I'm just going to say R equals, ray value takes 2 parts. It takes a position, and I'm going to call this one my just ray. And so I want to say it takes 2 things, $R.pause, and it takes a direction that it's going to fire the ray in, and that comes in a point of a vector again. So $R.transform row 3, which is our Z vector pointing straight down. So what this creates then is a ray value for us. So it creates this object with this ray value, and if we look at it, it returns 2 parts: the position that we set to it, and it returns the normalized direction vector, which is we're getting from the actual vector of our transform, pointing down. Okay, you'll notice it's actually mostly pointing down. Just to confirm that, let's rotate that so it's completely pointing down. We'll say 180, and run that and you'll notice now that it's actually pointing. This is basically 0 again because it's an exponent value. So our ray is pointing directly down along the z-axis. Now we're going to use a command called intersect ray EX. I think I've spelled that wrong. Yeah, right. And what intersect ray EX takes is two things again. I think it's the, I'd have to check, I think it's the object. And what we're going to do is we're going to just call this P for plain, make it real fast, simple. $P. We target the object we want to hit. Then we pass it the ray value that we want to fire at it. And that's very odd that we missed. Intersect ray EX. I have to think about this. $P. No, it's the ray. R is returning our ray value. And we're getting undefined for some reason. I hate when things happen the wrong way. Let me just load up intersect ray EX here. Intersect ray EX, node and ray. I don't know why it's not hitting. It should be hitting that. Somebody please tell me I'm nuts. Maybe because this is not, let's try the sphere. Sometimes you can get misses with this. And let's just call this R. And it'll probably fail on me as well. Oops, this is supposed to be P. There we go. Undefined again. Oh, come on. What am I doing wrong? Oh, that's interesting. I must be doing something wrong with intersect ray EX. Intersect ray will work as well, but not the one I would recommend. It isn't nearly as accurate. It will miss quite often. So it's working, so we'll keep going with it, and I'll try and solve why intersect ray isn't. So what intersect ray is doing is returning a ray value again. So that ray value, you'll notice, has a position and actually has another vector returned from it. And what it's actually returning when it hits the surface, it's firing a ray from this object, it's traveling down, it's hitting the surface somewhere, it's returning the point, the position that it hit the surface, and it's returning the surface normal as another vector pointing back out again. So what we can do is we can take our object we're going to be using for the target here, we're going to be targeting, I'm just going to call this T, and I can say, we'll call this hit ray, or just hit. Call that the hit. We can go $T dot pause equals hit dot pause, because it actually returns a position and a dir value. And again, that's pretty odd that it's way over there. There it is. So you can see that's right down and hitting right below it. So if I take our object I'm targeting with and our target object in blue and rotate that around and fire that off again, I'm firing that object right onto that point. Now what I can do is with the hit.dir is I can start to set its rotation values. So I could go and start building and looking at rotation values. So I could say Z equals, hit.dir, which will get me the direction vector of the hit. I can then set some upnode value. Let's say we're going to set x equals, and we'll hit it to an actual x value in world space. And then we're going to say y equals normalize cross product of the order, so it's zx, and then we're going to recalculate our up vector, x equals normalize the cross product of our y, z, and then I can create a transform matrix out of this, so I can actually say dot transform equals matrix 3 x, y, z, and hit dot pause. So if we calculate all that loveliness, let's get rid of that line, and we look at this point now, you can just see it aligned itself up. So it's actually calculating, hitting that. Oh, intersect ray EX needs a mesh. That's right. Thank you. So if I rotate that a bit more and fire it, you'll notice what it's doing is it's actually calculating a point on the surface. It's trying its best to calculate an up node of x at this point in time. And so we could have even used the up node of this object here, one that we're firing from, and getting it to line up to it if we wanted, so that we could have rotated it. So there's actually hit detection. Now this I use all the time, constantly using hit detection on stuff. If we look at tools like my pen rigging utils here, that's this isn't available, by the way. I've got tools that allow me to be able to stick things on surfaces all over the place for quick and fast setup of rigs and stuff. In this case, I can actually go in and say grid. Let's just put this on x0. And I want control objects stuck to the surface of an object, or at least to start with. I can actually go in and say put a control on the surface there and make me one on the other side. So it's actually just gone and fired those on and stuck them to the surface. They're not actually stuck. They're just to start with. And it's actually even mirrored the ray over and fired another one and stuck it to the other side. So it makes it really quick and easy for me to be able to create controls, for instance, for a face that need to be on it. And what I'm doing is I'm actually using a little bit of fun, and you can fire rays from your mouse. So if you look that up, I think that's even in one of Bobo's how-to examples or something. Firing a ray from the position of the mouse. And so I can fire rays right onto a surface. So this is really handy for sticking things down onto surfaces and whatever, just like the object paint is and whatnot. But in this case, I'm firing off one of my own functions that's sticking down a point helper and and putting a circle in the same place, linking the circle to the point helper, and then it even goes about freezing transforms on the circle. So it does a bunch of the work that I need to do myself. Doesn't work for standard primitives. The node stack has to be evaluated to a mesh. Yeah. So what you need to do is you need to make a copy of the mesh. $.mesh should return the correct thing. So we might want to try. So $.mesh might do it. EX runtime error. Requires a node. Try mesh. How do you have to do it again? You kind of capture it into memory. Huh. You got to capture it into memory, and for some reason I can't. It's eluded me right now as to how that's done. Maybe it's in the help file there. So you capture basically the object you're working on back as a mesh in memory, and then fire at the one in memory. And it's much more accurate though. The intersect ray EX is far more accurate for it doesn't hit run into misses basically very often at all. There's one more, and that's ray mesh intersect. Ray mesh intersect or ray mesh grid intersect. One of those two as well. You might want to look up. Those aren't any good for animated meshes, because what they do is they actually build a quad tree for the mesh and does much faster hit detection. So in my car rig that we were looking at, it actually has two modes: an animated ground surface or stagnant and stationary, and that's usually what you're using. And what it does, it's actually dicing it up into an octree the ground plane, so that it's not having to hit detect millions of polygons. It's only having to go for an area that it's in. Makes the hit detection much faster on larger meshes. This method here is always inspecting the entire model all the time, so it's having to look at the entire model. One of the things that Intersect Ray EX does when it hits, though, it doesn't return just a ray when it does it. It actually is returning 3 parts, and one of them is the barycentric coordinates, and we're going to get into that, but we're kind of run out of room. But quickly, a barycentric coordinate, if you take any triangle, is a weighted value between the 3 points on the face. You need that if you want to get things like UV coordinates, or if you want to be able to apply an attachment constraint, for instance. So if you want to be able to go animation constraints, attach constraint, and stick that on a surface, and then be able to set the position of it, it's actually attaching itself to a barycentric coordinate here. And so you can actually use Ray Intersect EX, and I've got that as well, that when you click on a surface, it automatically sticks things to a surface with an attachment. I don't know if you guys saw my bird demo for the feathers, where I can just paint feathers onto a bird and then calculate and manage them all. Called Bird Brain, and it was doing just that. As you paint it onto the surface, it was hit detecting the surface and essentially finding and assigning barycentric coordinates to attachment constraints. The KD tree David came into when you were painting the feathers, angles and combing them. When you're combing them, I had to build a KD tree to make fast searching possible on thousands of feathers. You know, I could real time with Maxscript paint on 6,000 feathers and calculate their angle of rotation needed by the brush stroke. That you start needing things like KD trees. So if you guys don't know does anybody know what an octree is or a KD tree is? Or what's the other way they put it? Voxels. If you think of dicing up your scene, if I have to hit this object, for instance, I need to fire at this object. You can kind of think of it this way. Let me just throw it in and explain it real quick. Grab my pen here. If you take this scene and you need to fire and need to hit something on the surface here, right here, you basically need to test everything. You need to say, well, have I hit this face? Have I hit that 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 face? Have I hit, and go through all of them. But what if I went and took the scene and or the object first off, and I did something like this, and I broke the object up? Because the first time I hit, well, that's fine, but if I had to continually keep hitting, it would be really slow. So what if I broke it all into boxes? We'll look at sort of a 2D tree here. And I took all of the vertices that landed in that area and I stuck them in this box, and all the vertices and all the faces that landed in this box and stuck them in this one, and so on forth. And then when I do my hit test, when I first fire a ray out, I actually say, which box do I hit? Well, I hit this box entirely. Now search all the faces inside that box and see if I hit one of the faces. I don't have to go through all of the faces in the entire object. All I have to do is go 4 by 4. That's 16 hits initially to start with, and then however many faces are inside of that, we'll call that another 8. Okay, and we've got 24 tests. Whereas if I had to test every single one of these faces, that's a whole lot of testing to do. So an octree becomes 3-dimensional. You know, you're looking at basically a 3-dimensional breakdown of your scene into these chunks. And an octree splits things in even areas. So each area is the same size, but the amount of things in each area will be different, possibly, right? You may only end up with one vertex or one face in one box and a pile more in the other. So your searches aren't evenly found. Let's see how this works. Erase all drawings. How about that? I have to go back to here to start drawing again. What the KD tree does is it says, you know what, let's actually not break it up evenly. Let's say there was more vertices on one side than the other. It actually would place the center lines, and then it basically breaks it down into sort of known planes of, you know, there's these plane cut slice through the model. Because there's more vertices on this side and this side, it's not on the center. And then it cuts another plane on another axis, Again, dividing it evenly. And then it goes through and it divides it, and it just keeps slicing and dicing it on the 3 axes until it's diced the model into a bunch of pieces. And when you go to hit test, you run through those pieces, and it's much, much faster. That's quick searching for working with models and whatnot. So I had to write that when I did the feather thing. So that was a bunch of fun math to figure that one out, let me tell you. That one hurt my brain. It was the first time I really had to do it in any serious amount, and it was rather difficult to do. I don't have Bird Brain installed right now, so I can't even show you it functioning. So that's it. We're at 1 o'clock. I think we've covered a pile. It's actually more than I've ever managed to cover in one of these classes. Let's take a few minutes and I'll field any questions or whatever. See if you've actually have any questions for anything here. Anybody? Everybody asleep now, or? So questions. If you don't have any, type no, so I know not to wait. Fair enough, Valmore. That's usually the case. I found the same thing. I've just got to go back and play with it all then and just hack on it and beat on it for a bit. Hopefully you guys have some time today to do that right after. The recording I'll try and get out within the week and out to you so you can watch this back again. When is the long format class coming? Not sure yet, David. I'm still waiting on final schedules at Humber College, so I need to know when they are before I can book anything. Kevin, I'm good on this. This is great. Glad to hear, Kevin. Hopefully Valmore and Kevin, we get to run into each other at some point, maybe in Toronto. I'm never there practically, but maybe one day at some event or something would be good, since you guys are in town. Try to make the intersect Ray EX work. Yeah, it's David. It works better. And again, try the Ray Mesh Grid intersect as well. And again, it's a little bit different to use, but probably as soon as I turn this off, I'll remember how to make the mesh. Yeah, if you converted the mesh to an editable mesh, it would work, correct. It would actually function, but you don't want to be doing that in your code because you could have modifiers on top of the stack and stuff that are turning it into an editable poly and whatever, and you don't want to keep destroying it. So you want to grab it in memory is the easiest way to do it. A parent constraint that I was working on, wow, that would have been a very, very, very long time ago. Very long time ago. Max's works reasonably well now, and with a little bit of code on top, the link constraint, it'll function. Yeah, the link constraint. And it's going to be faster than any of the ones I wrote, unless I start doing it in C++. Yeah, I was working on one, and it actually functioned. It worked great, but again, it was based on link script controllers and stuff, and there were sort of management issues with trying to calculate stuff and work with it. So it went into a few of my rigs for clients back when, but now I just use a link constraint because keys show up for it, right? So now I just have a function that manages my link constraints for me, a custom attribute definition that deals with that. That is right there. So that I can actually dump them onto it. So there's my link constraint management stuff that handles it all and makes sure keys stay aligned and all that kind of stuff for me. Anybody else? Okay, I'll try and get to checking that video, see if I still have one. I'd be surprised if I still have it on my drive, but maybe I do. And who knows? Maybe it's corrupt there as well. I don't know, but I can always redo it. I would think I've got the max file. I always store that kind of stuff. All right, guys. Thanks for coming out. Other guys were very quiet. I don't know if you either fell asleep or signed off. Thanks for coming out. Again, I'll try and get this class out to you as soon as possible within the week, hopefully. Please don't share it around. Just point people towards my master classes, and I'll rerun these things over and over again. So you guys have a copy of it soon. And take care. Enjoy your lunch or dinner or breakfast, whatever it might be at this point in time.